The exploration of Jupiter has evolved significantly over the years thanks to advances in telescope technology. Early observations relied on visible light, with instruments like the Hubble Space Telescope providing detailed images of the planet's clouds and storms. However, visible light has its limitations, as it cannot penetrate Jupiter's thick atmosphere or reveal what lies beneath. The arrival of infrared technology, exemplified by the James Webb Space Telescope, has opened new possibilities. Infrared wavelengths allow scientists to peer through the planet's clouds, uncovering hidden structures and dynamic processes. This shift from traditional optics to infrared observation marks a major milestone in our understanding of Jupiter's complex environment. Optical images capture light in the visible spectrum, allowing us to see celestial objects as they would appear to the human eye. In contrast, infrared imaging detects heat signatures, revealing details hidden behind dust and gas clouds that block visible light. The James Webb Space Telescope, or JWST, excels in infrared observation, enabling it to peer through the cold, dense haze surrounding Jupiter. This capability allows scientists to study the planet's deeper atmospheric layers and uncover phenomena that remain invisible in optical wavelengths. By using infrared technology, JWST provides a more comprehensive understanding of Jupiter's structure and dynamic processes, offering insights that were previously out of reach. The James Webb Space Telescope, or JWST, represents a remarkable leap in astronomical technology. Unlike its predecessors, JWST is specifically optimized for infrared light, allowing it to peer deeper into the universe and reveal phenomena that were previously hidden. This capability is especially valuable when studying Jupiter, as JWST can analyze the planet's temperature, chemical composition, and dynamic processes with unprecedented detail. By observing in infrared, the telescope can detect heat signatures and subtle changes in Jupiter's atmosphere that other instruments might miss. As a result, JWST provides scientists with a powerful tool to unravel the mysteries of the solar system's largest planet, far surpassing the observational limits of earlier telescopes. Infrared imaging of Jupiter's Great Red Spot reveals a new level of detail within this iconic storm. Fine filamentary structures and clusters of bright, small clouds have emerged, features that were previously undetected. These intricate patterns highlight the remarkable complexity of the storm system, suggesting dynamic interactions between atmospheric layers. The newly observed cloud formations offer valuable clues about the processes driving Jupiter's weather. By studying these details, scientists gain deeper insight into the mechanisms that sustain and shape the Great Red Spot. Such discoveries underscore the evolving nature of planetary science and our expanding understanding of Jupiter's turbulent atmosphere. The James Webb Space Telescope's advanced spectroscopic capabilities allow scientists to analyze the chemical composition beneath the clouds of the Great Red Spot. By examining the light signatures, researchers can detect specific molecular fingerprints. Among these, ammonia, phosphine, and water vapor have been identified within Jupiter's troposphere. These findings provide valuable insights into the atmospheric processes and dynamics occurring deep within the planet. The presence of these compounds helps scientists better understand the complex chemistry and weather patterns that shape Jupiter's iconic storm. Above the Great Red Spot, The ionospheric layer reveals a dynamic environment shaped by powerful forces. Scientific observations have shown that the Great Red Spot is not merely a surface phenomenon. Instead, it acts as a massive engine, lifting material from deep within Jupiter's atmosphere up to the higher layers. This vertical movement transports gases and energy, influencing the planet's weather and chemical composition far above the visible storm. The evidence suggests that the Great Red Spot's impact extends well beyond what we see, connecting the depths of Jupiter with its uppermost atmospheric regions. Exploring the complex structures within the ionization layer, the James Webb Space Telescope has revealed a surprising array of dark arcs, bands, and bright spots. These features challenge previous predictions that this layer would appear smooth and uniform. Instead, the observations suggest a dynamic environment where intricate patterns emerge from interactions between charged particles and magnetic fields. The presence of these varied structures indicates that the processes shaping the ionization layer are more complicated than once thought. Scientists are now re-examining existing models to better understand the forces at play. This discovery opens new avenues for research into the behavior of ionized gases in space. Gravity waves are oscillations that occur within a fluid medium, such as the atmosphere, due to the restoring force of gravity. In this context, energy generated by the Great Red Spot, or GRS, initiates gravity waves that propagate vertically through the atmosphere. As these waves travel upward, they carry energy from the lower atmospheric layers to the ionosphere. This vertical transmission of energy disrupts the ionospheric environment, leading to turbulence and the formation of distinctive structures. The interaction between gravity waves and the ionosphere can result in changes to density and temperature, ultimately shaping unique patterns in the upper atmosphere. Such processes highlight the dynamic connection between atmospheric phenomena and ionospheric behavior. Recent studies have provided compelling evidence for vertical coupling in Jupiter's atmosphere, particularly when gravity waves break in the ionosphere. As these waves propagate upward from the lower atmospheric layers, they encounter regions where their energy intensifies, eventually causing them to dissipate or break. This process releases energy and momentum, which in turn shapes the structure of the upper atmospheric layers. Observations from spacecraft and ground-based telescopes have revealed changes in temperature, wind patterns, and chemical composition that correlate with gravity wave activity. These findings suggest that the dynamics initiated in the lower atmosphere can significantly influence the behavior and organization of the ionosphere and beyond. The vertical transport of energy and momentum is thus a key factor in understanding Jupiter's complex atmospheric system. Wide-angle images captured by the James Webb Space Telescope reveal Jupiter's intricate system of moons and faint rings. Thanks to the telescope's exceptional sensitivity, even the smallest satellites and the subtle dust rings surrounding the planet become visible. These observations provide a clearer understanding of the delicate structures that orbit Jupiter, which were previously difficult to detect. The faint rings, composed mainly of dust particles, contrast with the planet's larger, more prominent moons. By highlighting these features, JWST demonstrates its ability to uncover details that expand our knowledge of Jupiter's complex environment.
As Io passes behind Jupiter, its fiery presence is temporarily hidden from view. Io is renowned as the most volcanically active body in the solar system, with eruptions that constantly reshape its surface. These powerful volcanic events eject vast amounts of material into space, feeding Jupiter's magnetosphere with charged particles. The interaction between Io's volcanic plumes and Jupiter's magnetic field creates dazzling auroras and intense radiation belts. Even while eclipsed, Io's influence on its planetary environment remains profound, highlighting its unique role as a dynamic source of energy and matter in the Jovian system.
The James Webb Space Telescope employs advanced observational techniques to study celestial bodies with remarkable precision. When Io, one of Jupiter's moons, enters an eclipse, JWST takes advantage of the darkness to directly detect thermal emissions from volcanic hotspots. This approach allows scientists to observe active regions such as Kanehekili Fluctus and Loki Patera without interference from sunlight. By focusing on Io during these eclipses, JWST can capture detailed infrared data, revealing the intense heat and dynamic activity of its volcanoes. These observations provide valuable insights into Io's geologic processes and the nature of its volcanic eruptions. Expanding our perspective beyond Jupiter, scientists have turned their attention to giant exoplanets orbiting distant stars. These massive worlds, often referred to as gas giants, present unique challenges and mysteries that differ from those within our own solar system. The James Webb Space Telescope, or JWST, has been instrumental in unveiling the secrets of these distant planets. With its advanced infrared capabilities, JWST allows researchers to analyze atmospheric compositions, weather patterns, and even potential signs of habitability. By studying exoplanetary gas giants, we gain valuable insights into planetary formation and the diversity of planetary systems across the galaxy. This ongoing exploration continues to reshape our understanding of the universe and our place within it. For the first time, scientists have successfully measured the chemical composition of a circumplanetary disk, the region where moons are thought to form around exoplanets. This breakthrough has led to the discovery of complex organic molecules within the environment surrounding these nascent satellites. The presence of such molecules suggests that the building blocks of life may exist even in distant planetary systems. By analyzing the disk's spectral signatures, researchers identified compounds that are essential for organic chemistry, offering new insights into the processes that shape moon formation. These findings mark a significant advancement in our understanding of how planetary systems develop and the potential for life beyond our solar system. The analysis of complex chemical structures, such as benzene and diacetylene, provides valuable insights into the origins of life. These molecules, found in various planetary environments, suggest that the formation of life may be an inherent feature of giant gaseous planetary systems. Their presence indicates that the necessary chemical building blocks for life can naturally arise under certain conditions. This discovery challenges previous assumptions about the uniqueness of life on Earth and opens new possibilities for its existence elsewhere in the universe. By studying these compounds, scientists can better understand the processes that lead to the emergence of life in diverse cosmic settings. Jupiter stands out not only as a massive planet, but also as a cosmic laboratory. With the help of the James Webb Space Telescope, scientists are able to study Jupiter in unprecedented detail, uncovering new insights about its atmosphere, composition, and dynamic processes. These discoveries extend far beyond our solar system, offering clues about the formation and evolution of countless distant worlds. By observing Jupiter, we gain a deeper understanding of planetary systems throughout the universe. The knowledge gathered here helps unlock the mysteries of other exoplanets, shaping our vision of the future among the stars.